going through in thinking about early planetary differentiation process, origin of volatile elements, and so on. And today I'm kind of going to give you some flavor of another line of work that we do in our group that is related to the ongoing differentiation of our planet. Sort of primarily like magmatism, devolatilization, subduction. So all the igneous core processes that many of you probably learned. Specifically speaking, I'm going to talk about evolution of continents from bottom up. As I mentioned in my group, we are dealing with a range of topics, but broadly under the umbrella in the sense of origin and evolution of life essential volatile elements, and thinking in particular about the interior to surface exchange and the cycling, geochemical cycling of this, and how the geochemical cycles are affected by interior processes. At the same time, how some of these geochemical cycles impart physical and chemical control in the interior processes, such as particle energy, subduction, volatile cycling, rheology, and so on. Right? So one thing, when we do that, we not only look at our own planet and the geological processes in our planet, we try to do similar things, of course, with much less data available to us. We try to look at other inner solar system planets through the same lens and try to ask ourselves, are those similar processes operating on Mars or in Mercury or on Venus, and what we know or what we not know, what are some of the commonalities or differences, right? So when we are talking about commonalities or differences between between our inner solar system planets, and specifically if we talk about Earth, Mars, and Venus, some of the very basic data that we can observe right away is the hypsometry, which basically is telling you about the elevation of the surface of the planet or how much that elevation varies from the mean elevation. So what you are looking at here is the hypsometry or the elevation range for planet Venus, elevation range for planet Mars, and that for our own planet Earth. And one thing that stands out is both for Venus and Mars, as you can see that overall there is one peak in the elevation, surface elevation of the planet, right? So that means although Mars has a bigger range than Venus, the topography doesn't have a dichotomy. However, in our planet, as you can see, that hypsometric curve has a bimodal distribution. What is that? What are these lower peaks representing? The lower peaks are representing ocean basins because we have deep ocean basins. And the higher peaks are representing what? It's mountains and the lands we are standing on and having these lectures and conversations, continents. Right? So we have continents and ocean basins in our planet. We don't at least have observed it in any other planet so far. Definitely not in our solar systems. And of course, we don't have similar data from our solar systems. Right? So in that sense, having continents, it's a unique feature in our planet. So actually, since starting my academic and research journey, I have never worked on continents. Right? So I thought, okay, that's a unique feature compared to planetology tells us continent is something that's special to our planet. Other planets don't have it. So I said, okay, I first want to learn something about continents if I am going to work on it. So first thing I do, being lazy rather than reading up anything, I just Google, oh, it's a continent. So a Wikipedia page comes up telling me what are continents. As you can read, a continent is defined by continental crust, which is a platform of metamorphic blah 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 igneous rocks, largely granitic composition, and primarily continental crust is less dense and much thicker than oceanic crust, which causes it to float higher than the oceanic crust on dense underlying mantle. So I said, okay, and it goes on to say, this explains why the continents from high platforms surrounded by deep oceans. I'm like, okay, that's correct. It says that, like, but is it the only thing that makes continents special? Or the elevation of the continents? So then I went on to Google the term cratons. Many of you probably have heard that. It's nothing but the core region of continents, the central part of continents that we think have remained mostly unmodified over geologic timescales. I said, okay, what are cratons? Again, Wikipedia first tells me that the term craton is used to distinguish stable portion of continental crust from regions that are more geologically active and unstable. I said, okay, that's true. But as it turns out, neither of these two definitions of continents, not that they are incorrect, but I would say they are incomplete. Why they are incomplete? And especially for cratons, they are incomplete. And why is that? Then it's not like I'm not picking on Wikipedia. by the way. Wikipedia did to the right stuff. What it then said, a craton is an old and stable part of continental lithosphere, which consists of Earth's two uppermost layers, the crust and the uppermost layer. So when you are thinking of continents, and specifically that older portions of continents or cratons, especially its elevation, you need to look at the lithospheric mantle part, the subcontinental lithospheric or subcratonic lithospheric mantle part, as well as the crust together. Their buoyancy and elevation is not just aided by the crustal part alone, it's also aided by that deep cratonic mantle root, which is buoyant and less dense. And that's what makes continents stand up the way it does. So I said, oh, that's good. Now I am closer to my territory of understanding mantle processes, so I can do something about it. So why do cratons appear to be stable over billion years? It's one of the questions that geologists or petrologists have been wondering for quite some time. And the primary reasons the continents or cratons appear stable and point is that continental mantle root beneath old part of continental crust. They are chemically buoyant and they are mechanically rigid, so they float. What type of evidence do we have that they have those chemical features? What I'm showing you here to the left is the probability density function of magnesium number of mantle peridotite rocks. So these are the rocks, green colored olivine minerals in there, as you can see in that picture. These are the rocks that make up all of our upper mantle, most of our mantle. There are some small heterogeneous. And what is plotted is the Mg number. And if you are not familiar with what is an Mg number, it's simply a way of representing magnesium to iron ratio of mantle rocks. What you can see in the ambient mantle, meaning mantle that is beneath oceanic basins, the Mg number of olivine is around 89, 90 of that range. However, if you look at peridotite xenolith dominant compositions beneath cratons or beneath old portions of continental crust, their Mg numbers are much higher, around 92 or so. What that tells you is more partial melt has been extracted from it, making the Mg number go up, and because more iron has been extracted from it, the mantle is now more buoyant, less dense, and that contributes to the elevation of continents. And that's kind of another way of showing. So if you go with Mg number of 92, as you can see at standard temperature and pressure, the bulk density for peridotite rocks is much lower if it's Mg number of 92 as opposed to if it's Mg number of 89, right? So olivine or peridotite rocks will be less dense if it's more refractory. It will be more dense if it's more fertile. It's kind of pretty basic. We knew that all along. There's just a justification. So again, cratonic lithosphere is cold, thick, and rigid. There are lots of evidence in support of that. The first diagram here is showing a pressure temperature plot from the work of my colleagues Lee and his students and colleagues. What that shows you what type of thermobarometric estimates we can extract from doing petrology on these type of rocks. And what it tells you is, of course, we don't have lots of data. We have limited availability of these xenoliths, but that tells you that the heat flux that is relevant beneath cratons is relatively cooler, and accordingly, if you propagate these conductive geotherms with that of the ambient mantle geotherm, what you get is this intersection, which is roughly going to track the depth of the lithosphere boundary beneath continents or beneath stable portions of continents or cratons. So that's what we will call cratonic LAB based on petrological constraints. There are similar constraints based on geophysical evidence. So what I'm showing you here is again depth versus seismic shear wave speed beneath oceanic basins as compared to continents. And as you can see, that continents over a large depth range is characterized by relatively high VS, and their dip in VS sort of probably marks what we will call LAB potential. Right? So there is seismic evidence that the LAB is thick beneath continents. There is petrologic evidence, and there are some rheologic argument also that there is a jump in viscosity as you go from asthenospheric convective mantle to lithospheric subcontinental mantle, and there is a orders of magnitude jump in viscosity. So that means the continental mantle is not only depleted in iron, but it is also depleted in water perhaps, which rheologically strengthens it. So mechanically much more rigid as well. So these are kind of some of the features that tells us that lithospheric thickness beneath stable cratons are relatively thick compared to ocean distance. And that explains the relative elevation of continents compared to ocean distance. So the question is, are cratons stable over billions of years? Or are there ways of potentially losing the thickness of the continental lithospheric mantle or the crust in the process? As it turns out, like from regional studies, there are some evidence of losing that mantle keel beneath cratonic regions. This is an example from North China Craton, where older xenoliths that come from as old as 400 million years ago or so on, that bring up mantle xenoliths with diamonds, that tells us that the mantle lithosphere at that time period beneath North China Craton was relatively thick. But then we also have basaltic volcanism that are fairly young, that gives the depth of magma generation as shallow as 75 kilometers. What that tells you is for North China Craton, there is a draw in the lithosphere asthenosphere boundary, or sort of diminishing depth of that lithosphere asthenospheric boundary as much as 150 kilometers. So that means somehow the cratonic keel, the mantle keel, the lithospheric keel beneath North China Craton has been eroded through some process. This observation doesn't tell you what the process is, but it tells you that likely it happened. So the question is, do cratons remain stable globally over billions of years? We have evidence like North China Craton, and there are a few other examples like that, that tells you that locally there may be loss of that subcontinental lithospheric mantle, especially in portions of cratons. But the question is it a global phenomenon? Is the cratonic root of all cratons globally is gradually getting thinned down? We can't do that just from one location. And the second question is, if that is happening, what may be the cause of destruction of cratonic geology? And there are many different ideas, such as metasomatism, or basaltic underplating, or melt underplating, that makes the base of the lithospheric mantle relatively dense and eventually it founders. There are ideas about related to tectonics that you perhaps it's like a convective thinning. Sometimes you compress and then eventually it gets so deep that it becomes dense and then falls off, like Peter Molnar and others. There are ideas related to HGO-induced geological weakening, that there is processes such as subduction, which supplies aqueous fluid that implants at the base of the lithosphere, eventually making it less viscous as opposed to more viscous, and rheologically gets weak. And over time, convection process can remove that rheologically relatively weak boundary layer at the base of the craton. So there are many different ideas, and people have explored this. This is not me. It's kind of just summarizing what has been hypothesized before. Now, in terms of trying to find a global trend, if there is any, in terms of that thickness of cratons or the cratonic lithospheric mantle being constant over time, or decreasing over time, or increasing over time. If you want to get some systematics globally, we need some sort of a probe that allows us to probe the possible lithospheric thickness of different ages in different cratons all over the world. Right? The problem with peritotite xenolith based studies is you can do it, but in certain regions where you have good coverage of xenolith samples that allows you to draw that conductive geotherm and identify the conductive geotherm, convective geotherm intersection, identifying that LAB boundary. But in order to do that, you need to have good representation of xenoliths coming from all different depths. As it turns out, we have this in certain locations, but we don't have xenolith coverage of different ages, especially from all different cratons. We have sporadic samples, right? So peritotite xenolith-based thermobarometry will be very useful, and that's the traditional approach, but that gets limited when we are talking about tracking the time evolution of continents, because we don't have xenoliths of all different ages. And that's some kind of talking about here, that what is the limitation of xenolith-based approach. So one I mentioned already, limited sample. The other thing is there is also some sort of thermochemical perturbations and diffusive resetting for some of the thermobarometers. You're probably fully aware of this. If you do RDE-based thermometer, sometimes it gives you a higher temperature, better thing, because it has a higher blocking temperature and so on. So FEMG plus cation-based things that can get reset if you have thermal overheating. So it's very powerful. That has been a traditional approach, but again, there are some limitations. So what we got interested is, if we are going to be doing something useful in tracking the lithospheric thickness beneath continents, we need to come up with some other tools. So we said, okay, what about looking at some melts or magmas that erupt specifically in continental settings, primarily in cratonic settings. And then we said, okay, one type of melt that is kind of unique to cratons and generally not observed in ocean basins are these magmas that we call kimberlites. So some of you may know what are kimberlites, not all of you may know. These are very strange magmas. These are not your garden variety basalts that erupt on ocean basins. These are very, very volatile-rich. They are very silica poor, and I'll show that in a later slide. But the good thing about kimberlites is they rapidly erupt to the base of the lithosphere. So they equilibrate at the base of the lithosphere, but erupt very, very rapidly. So they have a limited interaction, that's at least the conventional idea, through the lithosphere. So that means if we can come up with the depth of generation of kimberlite, there may be some way of correlating that with the base of the lithosphere, or the lithospheric thickness, if that's their last equilibration. They carry diamonds from deep interior, but they also may have the problem of sometimes getting contaminated by assimilation process, volatile degassing, alteration. So in order to use kimberlites as a probe, especially measuring the compositions of kimberlites, you have to look closely about compositional alterations, or is it really representing primary magma compositions? But I was like, okay, we'll give it a try. Using kimberlites some way. The other advantage of kimberlites is, of course, not only they erupt from great depths from the base of the lithosphere, and they are unique to cratons, they also have a pretty good age distribution. Although their frequency seems to be increasing in recent times and less common in older times, which partly can be something biased, but partly can be true increase of kimberlitic magmatism frequency in more recent times. But importantly, for our purposes, if we can find kimberlitic samples that allow us to somehow probe the depth of their generation, we can do this over as much as 2 billion years of our planet's history. So that means kimberlites might be able to tell us not only the cratonic mantle thickness, but the evolution of the cratonic mantle thickness through time over 2 billion years time period. So that was one of the reasons why we were thinking of kimberlites. Again, as I mentioned before, kimberlites are these relatively low silica magma that gets generated in the atmosphere, but then finally gets final equilibration happens at the base of the lithosphere, then it erupts. What I'm showing you here is a very simple classical igneous total alkali versus silica diagram, just outlining the point that kimberlites are very unique in terms of their measurable chemistry. They are relatively low in alkali, but most importantly, they are very, very low in silica compared to mid-oceanic ridge basalts, primitive arc basalts, primitive OIBs. As you can see, kimberlites plot in a very distinct measure element composition space. So what we need in order to utilize kimberlitic magma composition to probe their depth of generation is we need some sort of a thermobarometer that is based on kimberlite magma composition that will allow us to estimate the pressure and temperature of kimberlitic melts with mantle samples, right? Now, as it turns out, there are some melt composition based barometer that have been devised before, where people have done is they have utilized the silica index, or basically the activity of silicon in the melt, to be correlating with the depth of their generation. And this concept comes from the fact if mantle melts are generated in equilibrium with olivine and oxidioxins, which are reasonable assumptions, most of the magmas in our mantle gets generated in the presence of olivine and oxidioxins, then activity of silica should diminish with increasing pressure, because otherwise it's buffered by that assemblage. So silica index should drop, although the activity will be constant. So based on that, it has been shown that okay, we can potentially use the silica content or mole fractions of silica in basalts as a proxy of depth of generation. So low silica melts should be coming from deeper depths, higher silica melts should be coming from shallower depths. So when I say melts, I'm talking about basalts. Okay? But the problem of applying a melt silica activity-based parameter to kimberlites is the fact that kimberlites are so low in silica content. In order to stabilize that type of low silica melts, you need very, very high amount of CO2, primary CO2 to be dissolved in that melt. What I'm showing you is an experimental compilation of partial melt compositions that are generated from mantle lithologies in the presence of CO2. And what you can see is, in order to generate melts that are relatively low silica, the primary CO2 content of those melts need to be very, very high. Okay? And importantly, this correlation, this inverse correlation between melt CO2 content and melt silica content is actually holding true across a wide range of pressure, all the way from 2 GPa to 10 GPa or beyond. So that what that means is, if you are trying to utilize silica activity in the melt as a proxy for pressure, you will get some erroneous results, because the silica content may be simply lower because it has higher dissolved CO2, not because it's generated at deeper depths. So you can get some numbers if you try to apply silica activity based parameter to kimberlites. You will just get spurious data, because it may be real pressure effect, or it may be simply CO2 effect. Right? So we need to do something different. We need to not rely on this silica activity based parameter. And this is basically the point I was just trying to make. This is just showing you silica in experimental partial melts, and y-axis plot the predicted pressure based on applying silica activity-based barometer and the actual experimental pressure in GPa. What you can see is, as the silica content of the experimental melts are lower and lower, we know them from our experimental water, the predicted pressure and the actual experimental pressure, their difference is like huge. What that tells you, you just can't use silica activity-based barometer in low silica melts. And by the way, I'm not picking on these studies. They didn't devise their barometry to be applied to low silica melts. It's just a demonstration that those calibration systems don't work. You shouldn't use them for low silica melts, especially if the magmas are generated at sort of 70 kilometers or deep in the garnet sediment. So this is where our new work came in, developing a new liquid composition-based thermobarometer. This is the work of my former postdoctoral researcher, Cheng Wong Sun, who is now a faculty member at UT Austin, doing great work on his own. What Shane and I showed, again, this is the point I already made. If you plot the oxides in the melt as a function of experimental pressures, so these are not new experiments, by the way. This is just a compilation of all different experiments people have done, partially melting mantle rocks and documenting their partial melt compositions. When we do that, as you can see, the silica content as a function of pressure is all over the place, because it has variable amount of CO2 content dissolved in it, water content dissolved in it. So that correlation between silica dropping with increasing pressure goes away when you are looking in the volatile-rich systems. However, maybe that blue outline is not very clear, but what you can see, if you plot aluminum as a function of experimental pressure, alumina content of melt actually does show a negative correlation with pressure. And the reason we thought that might happen is, if these pressure ranges, sort of 2 GPa and higher, we are dealing with roughly garnet stability field. So you can kind of think of an exchange reaction involving the pyro component of garnet and MgO in melt, giving the phosphorite content in olivine and alumina content of melt. So alumina content of melt may be a proxy of pressure. And similarly, and this is not new, the MgO content of the melt will be a proxy for temperature, because MgO tends to be tracked. So we thought we would develop a new barometer primarily, but just for self-consistency, we'll devise another thermometer as well. That will be particularly relevant for melts that are relatively CO2-rich, as high as carbonated melts, like 40% CO2 and so on. Relatively wide range of water content, alumina content, over a wide range of pressures and temperatures. So what I'm showing you here is the robustness of the calibration we came up with. I'm not showing you the equation. If you read the paper if you're interested. What this is showing you is the difference in the actual experimental pressure and our predicted pressure based on that liquid alumina content based barometry we developed. And as you can see, our uncertainty in the pressure prediction is now down to half a GPa or so. So much better than the huge uncertainty we were looking at before. And temperature-wise, we can also retrieve experimental temperatures within sort of 50 degrees Celsius. Right? So we have a reasonably well-calibrated melt composition-based thermometer and barometer that now we can apply to any silica undersaturated materials. So in this study, what we did is we will apply to kimberlites. That's how we started. Because, right? We wanted to probe kimberlites or cratonic stability. So, but before we apply that, what we needed to do is we needed to have a robust global compilation of major element composition of kimberlites. So what this map is showing you is from our compilation, what we did is all different kimberlite cluster location, both on craton setting as well as off craton settings from all these different regions of the world that we compile in our compilation. Then after compiling those volcanic kimberlite databases with known location, known eruption ages, we also went through heavily in filtering, sort of looking for possible evidence of aqueous alteration, messing up the kimberlite magma composition, possible indication of alterations, assimilation or fractionation. So once we did that, we also fractionally corrected those magma compositions to be in equilibrium with the mantle olivine of 89 plus or minus 2 first-rate content, so that we get truly primary kimberlitic magma compositions that are supposed to be generating in the mantle. And then we were going to apply our chronograph. Just as a demonstration purpose, what I'm showing you here is two specific locations in Kalahari Craton, let's say, and Premier Kimberlite. And what I'm showing you is in these two locations, we previously had thermobarometric results from cratonic xenolith samples, outlining the convective geothermal constraint for those two cratonic locations. And what you can see is our predicted kimberlite composition based predicted pressure and temperature for the lithospheric mantle is right along the extension of that trend. We are going to get slightly deeper depths and slightly higher temperatures because kimberlites are, again, not getting reset through diffusive equilibration within the lithosphere. It's erupting straight from the base of the lithosphere. So we will argue it's more accurate representation of the true LAD depth in those settings. But what it's giving us is giving us confidence that after all, what we are capturing in both locations are broadly consistent with the trend, cratonic geothermal trend that we are getting from general samples. So this is just a demonstration purpose, but then what we wanted to do is not just apply to one or two regions in the world, apply it to our entire database. So that's what we do here. What I'm showing you, it looks busy, but what I'm showing you is pressure on the y-axis with pressure increasing downward, meaning with depth, temperature increasing to the right. There are a few things going on here. This is the peritotite solidus on a volatile-free basis. This is the peritotite solidus or the carbonation freezing front. If you have some amount of CO2 in the mantle, that allows you to generate relatively CO2-rich carbonic or kimberlitic magmas at temperatures that are much lower than the solidus. And then what I'm plotting are all different symbols for individual kimberlite compositions, and then by blue and the yellow, we are plotting the average compositions of clusters on craton and off craton, okay, for all these kimberlites. So those are average points of all kimberlite samples from one location, like we are calling them clusters. The thing that is, of course, it's giving a big range, so there are 1400 plus filter samples, so it's giving us a wide range of equilibration pressures and temperatures, all the way from 2 GPa to as deep as 10 GPa, like 300 kilometers. But one thing that is consistent is these pressure temperature domain of their generations are coming between the carbonated peritotite solidus and the CO2-free or water-free peritotite solidus. And that's exactly where we expect them to form. They are forming in the presence of CO2, so they should get generated at temperatures above the carbonated peritotite solidus, but below that of the dry solidus. So again, kind of another confirmation we are not off in terms of our estimations. But again, this is plotting kimberlites from all different cratonic regions shown on the map, but importantly, all different ages. But as I told you before, these are all volcanic kimberlites that we compiled. They all have known ages of eruption. So now what we can do is we can take this data and plot as a function of age of their eruption. And that's what this is. This is now we are plotting as a function of age the lithospheric thickness. So what is lithospheric thickness? We are now taking those melt mantle equilibration depth from kimberlites as a proxy for LAB depth. And that's a reasonable thing. Most petrology would say that the multiple saturation, that's the final equilibration. And then the kimberlite erupts very quickly without much interaction. In this particular plot, we are only plotting cratons where there were more than one kimberlitic magmatism episodes temporally separated. That includes Dharwad, Baltic, Wyoming, Slave Province, Kalahari, North China, and so on. And as you can see, when we compile everything, there is this broad trend of lithospheric asthenospheric boundary or the LAB depth being very, very thick are yawn and thinning with time. From this, what we are inferring that there is a possibility of lithospheric thinning with time, with thicker lithosphere getting documented at earlier time and thinner lithosphere in more recent times. Of course, as you go back in time with many studies, as we know, our samples get limited, so you'll have to always take this type of studies or results with a grain of salt. At 2 GA or 1.9 GA, there are only a couple of samples, right, coming from Baltic. But what's interesting in this particular plot is even if you look at one location rather than compiling everything. So if you look at, for example, slave province or Kalahari with these symbols, that even in one cratonic regions where there are multiple episodes of kimberlite magmatism with time, there seems to be some thinning getting recorded even in one region as well. Not just, so it's not an artifact of global compilation with different things, even potentially in one region, we are seeing that. That's not always the case, but there are certain specific cratonic regions where we did have more than one kimberlite samples of different regions where we did not find any clear evidence of lithospheric thinning. So in the green here, I'm still showing you that broad band from the previous plot, but these new samples from these locations are suggesting that either there is no discernible change in the LAB depth or maybe even thinning, right? So locally, there may be things that are not exactly what is being tracked in global settings. So it's not completely solid in a way. There are certain regions that are define that overall trend that I just showed you in the previous plot. But then when we look at all data together, meaning now we are not even filtering based on kimberlites erupting in the same region multiple times at different time periods. I'm even now looking at samples where there is just one occurrence of kimberlitic magmatism at one point of time. Again, when we plot those data at least as a whole still track that green band we showed you, meaning we actually prefer based on that there is probably some evidence that at least in domains of kimberlitic activities, the lithospheric thickness is diminishing with time. So many cratonic roots are being eroded away, at least in domains of kimberlitic magmatism. So, do cratons remain stable globally over billions of years, at least based on this analysis or the barometer application of that barometer to kimberlites? Our short answer is no. But of course, with caveats that not all regions are necessarily tracking that, so we have to think about other processes perhaps. So then the next thing is what may cause the destruction of cratonic lithosphere. As I outlined, we saw this slide before, I outlined different possibilities. Now, in this case, what may be the most plausible cause? Okay. So our barometric directive will not tell you what is the reason for that potential decrease in the lithospheric thickness, but we can still speculate based on some further analysis. So one more thing that we got out of this treatment is, remember, not only we developed a new barometer, but we also consistently developed a new magnesium oxide in the melt-based thermometer that you can apply to kimberlite magma composition. When we do that and apply to all our kimberlite samples coming from different ages, now I'm plotting a mantle potential temperature that we would estimate based on that melt temperature that we can calculate from kimberlites. What all these data points are those kimberlite-based mantle potential temperatures we estimate. What I'm plotting for comparison is the ambient mantle potential temperature evolution based on plot Hertzberg's work, which suggests that there may have been a secular cooling of the mantle coming from much hotter mantle temperatures at earlier times to relatively cooler temperature at the present day. What the kimberlites are showing you here is there is a broad correlation that is tracking that same evolution. However, with one important distinction, the kimberlitic temperatures are either overlapping with the ambient mantle temperatures, but in certain cases they are hotter. So based on this, what we kind of argue that the kimberlite generation requires either ambient temperatures or may even be mantle bloom type of settings, where the temperatures are higher than the background.
This ambient mantle temperature is litospheric mantle or
convective mantle. Convective, sort of morph mantle reference. So if you take that results at its face value, that the kimberlite generation requires at least ambient mantle temperatures or hotter, then thermal magmatic processes at the cratonic root may be one cause of causing that gradual erosion of the root and thing. But again, it's just you always know that just because two things correlate doesn't mean it's a causal link. So it just says it's a possibility, but you can of course prove it. But at least the temperatures are hot. So there could be plume impinging on the base of the lithosphere, generating kimberlites, and that's also causing the thinning process of that supply. There is another interesting possibility, and when we look at the thinning of the cratonic lithosphere with time, with the actual frequency of kimberlites, there is this interesting correlation, right? That when the lithosphere is thinner, there are more kimberlites being erupted. When the lithosphere is thicker, there are less kimberlites being sampled. Now, of course, kimberlite there could be a preservation bias. Older samples may be altered or eroded away and so on. I'm not saying I can deny that or refute that, but there is another possibility that because kimberlite generation, remember I told you these are CO2-rich magnets. So kimberlite generation requires supply of CO2 to the mantle source. Otherwise you can't form kimberlites. So is there a possibility that the deep carbon flux through subduction actually increased through dust? Meaning carbon being supplied by some deep subduction process was less efficient early on, more efficient in the Phanerozoic or in today's time. And that is causally linked to greater propensity of kimberlite generation in recent times, like less so early. Okay, that's another idea. And as it turns out, and this is the study by, we were talking about it yesterday, Holder et al. Study in Nature that talks about, and again, I'm not saying it's right or wrong, the suggestion from that study was that there is a decrease of the metamorphic thermal gradient with time from greater than 2.2 GA to more recent times. What that means, if that is true, what that means that the subduction was warmer and flatter early on, and it's now cooler and potentially deeper with more recent time in modern era. If that's the case, that will be consistent with our idea of putting more carbonates down the subduction channels in more recent times, supplying the mantle source regions with CO2 that will be needed for your kimberlite generation, and that process being much less efficient early on in ancient time. And accordingly, kimberlite generation was less, thickness of the craton was thicker, and allowing kimberlite reduction to be even less so, because thicker root, kimberlites are not enough supply. So if this is the case, not only that thermal plume model is interesting, there is potentially an idea that kimberlites are also directly causing some weakening of the root of the cratons. What I mean by that, in most of the cases that CO2-rich melt gets generated at the base of the cratons, because that's exactly where the cratonic geotherm intersects the carbonated crater exolysis. That's kind of coincides with the LAB. But in most cases, those melts probably just hang out or freeze and don't erupt, because it needs to, after all, go through a very, very thick cratonic root. In occasional cases, they do go through it and we have a sampling of kimberlite, sometimes with diamonds and so on. But in other cases, they just hang out. We call them kimberlite hibernation zone, sort of hanging out there. But in the process, because the kimberlitic melts are relatively CO2 and water rich, not only they can supply water to the ambient, or not ambient like that, base of that relatively buoyant lithospheric mantle and rheologically weaken it in the process. So of course there is this classic study by Hart and Kolstedt which showed that the viscosity actually drops a lot going from dry grade type to wet grade type. So if kimberlite magmas are also hydrous by kimberlite generation at the base of the lithosphere, and if those melts are metasomatizing, one effect would be rheologically weakening the base of the lithosphere. And then it's easier to convectively remove that base because it's now rheologically. So that's another idea. So some take-home message from this is a new melt alumina-based parameter is developed for CO2-bearing naturally derived magmas. We applied that for global kimberlite compilation, and what that shows The younger kimberlites are yielding shallower equilibration depth, older kimberlites are yielding deeper equilibration depths. What that may mean is the cratonic lithosphere is likely getting thinned by as much as 150 kilometers over 2 billion years, and this is a process that's happening globally. When I say it's happening globally, of course, again, I'll caution you, we are only documenting this in regions of kimberlitic magmatism. So is it really happening globally through some processes, and kimberlites are just allowing us to probe that in those spots? Or is it really happening, causally being linked to kimberlite generation? If that's the case, it could be that the topography of the base of the lithosphere is actually undulatory, and yes, it's getting thin with time only in regions of kimberlitic magnetism, but maybe not elsewhere. We don't know which one is the case, because after all, we are only probing it in domains of kimberlite sampling. Right? And this process can happen either through thermomagnetic processes like plume, or it can happen by rheological weakening, which is the latter one is slightly a different model, because in that case you can invoke this process to be operative not just in cases where the kimberlite temperatures are hotter, but even in all kimberlite cases where it's even matching with ambient manifold. So with that, I probably should stop. I just had one more little thing. Are you guys 5 more minutes? Okay. So then one more thing I just wanted to quickly point out is that was all good. But now if I bring it back to this plot, you may recall that although most of the average compositions plotted at ambient mantle temperatures and above, there are some samples, individual temperatures, that also give relatively shallow equilibration pressures and temperature. What that means that maybe not most of them, but there are some fluids and volatile-rich melts that are equilibrating not at the base of the lithosphere, but within the lithosphere, meaning it's percolating up and getting equilibrated within the lithosphere. That's not the best news for our kimberlite story, but then that gave us a thought process. So there could be some sort of a melt rock interaction happening within the whole lithosphere itself, some sort of reconciled. So then we asked ourselves the question that are there any evidence for volatile-rich metasomatism, maybe aided by kimberlite melts. So this is the work of my former PhD student, Stefan Saha, who did a nice study. And actually, by the way, the study that I will show you involved Maina Kuperji, who I believe you guys, this was done in collaboration with him and one of his students, EFN. So we looked at this concept that is actually observed seismically. It's called mid-lithospheric discontinuity. This is a very strange feature, and I am being told, and in many conversations I had with seismologists, that it's a controversial observation. Not all seismologists necessarily believe it. Or this is coming mostly from receiver function data, where seismologists observe a dip, potential dip in the shear velocity at depths that are way too shallow for it to be a regular. So there is another dip at greater depth which they interpret to be lithospheric, astrosphere boundary. But at mid-lithospheric depth, somewhere between 80 to around 150 kilometers or so, they see another small dip in VS, which they interpret as mid-lithospheric discontinuity, meaning some process that's causing the VS to be lower. Now, one of the hypotheses for mid-lithospheric discontinuity is that maybe it's causally linked to craton formation models itself, or craton formation process itself. And in that craton formation process, there are a number of them, such as the slab imbrication or sort of arc thickening and accretion models. In many of these settings, if you follow the process conceptually, the lithospheric mantle generation may also be coupled with some sort of fluid and melt addition as well. Although overall it's depleted, but there is no decay melts that may get in front. So one of the things we asked ourselves, so if there is a flux of hydrous carbonic or kimberlite melt or flux of fluid, can within lithosphere processes stabilize volatile bearing mineral pieces in that interaction process, such as formation of amphiboles or chloroplastics and carbonates. And the interesting thing about the stability of those phases, they all have intrinsically lower shear load speed. So even small amount of those phases can potentially cause a broad aggregate reduction of yields. So we wanted to ask ourselves that can we stabilize amphibole or prophyte or these spaces, and more importantly, can you stabilize enough of those? So after all, the absolute magnitude of reduction is related to the modal abundance of those spaces. Can there be enough of those spaces that you can explain something like MLD by this type of phases? So what we did here, again, it's not a new experimental study. It's mostly based on, not mostly, it's actually based on compilation of existing high pressure temperature experiments of peridotite in the presence of H2O or CO2 or both. All we wanted to see is, as a function of pressure and temperature at depths similar to MLD conditions, what phases are potentially stabilized just purely by thermodynamic equilibrium, phase equilibrium, and if so, how much of that can be stabilized. So what I'm showing you here are possible presence of either amphibole or phlogopite or both. So if one side is dark, means that phase is not present in that experiment. The other phase is present. If there is no dark side, that means both phases are present, amphibole and phlogopite. And it's color coded with bulk K2 to H2 ratio. So it's very simple. If the bulk K2 to H2 ratio of the bulk system is higher, you tend to have more phlogopite being stable. If the bulk K2H2 is relatively lower, you tend to have more amphibole being stabilized. So it's kind of very basic phase chemistry in the peridotite system, but still it's kind of good to see that once you compile that. What came out of it is parasitic amphibole and phlogopite are the two most plausible hydrous phases that can be stable at MLD depths. It's not chloride, because the chloride boundary is much lower temperature. It's not any other exotic phases. And in order to have a lot of carbonates, you need a high amount of CO2, which we don't think is reasonable. So we mostly focused on pargasite and phlogopite being the two plausible phases that can cause this reduction. Now the question is, okay, these two phases can be present, but how much of it can be present? Because after all, the reduction will be again correlated with the overall modal volume, or the modal proportions of these phases. So the next thing we looked at is again two things. We compiled natural cratonic peridotite compositions from all over the globe, saying, okay, what is the most dominant compositional range at MLD depths for cratonic peridotite? And what we found out is the calcium content of cratonic peridotite compared to experimental compositions are generally much lower. This is the peak, the red peak here. And same, the K2 contents are also very low. Why these two oxides are important? What we found out from our experimental compilation is the overall modal abundance, or the mass proportions of amphibole and phlogopite, they show a broad correlation with bulk CO content for amphibole and bulk K2O content for phlogopite. And again, you would expect that, right? Pargasite amphibole should correlate with bulk CO content, phlogopite should correlate with potassium content, right? So what that means is these gray bands and this particular spherical gray band is the most dominant mode of cratonic peridotite compositions. So if the bulk CO content, which is relatively low in STLM or subcontinental lithosphere mantle, and the bulk K2O content is so low as observed in the natural samples, although we can stabilize amphibole and phlogopite, you cannot have much of it. You can have at max 10% of amphibole or less. You can have at max of 5% of phlogopite or less. So you can't have more than that. So then what we did, and this is where the physics approach came in. What we did in this study is systematically calculate the elasticity of all the relevant end members that are needed to calculate the aggregate shear wave velocity consistently for subcontinental lithospheric mantle type of composition in the presence of phlogopite, pargasite, or magnesite. And that's what I'm summarizing here. So the aggregate shear wave velocity calculated with nominal physics data or new compiled data that are filtered, and we plot that as a function of mode of amphibole or mode of. As you can see, as expected, if the mode of amphibole is higher and higher, and these are again the phase equations are coming from experiments, the mineral physical data are allowing us to calculate the PS. What you can see is as the mode of amphibole or the phlogopite increases, there should be a drop in the aggregate shear wave. But importantly, because the mode of amphibole cannot be more than 10%, and the mode of phlogopite cannot be more than 5%, for natural systems, the And what we ended up concluding is a fraction of that can be caused by sulfide and amphibole, but not all. So the take-home message from that latter part is volatile-induced modal metasomatism within cratonic crystalline mantle. Of course, can happen, but has to be limited in terms of total modal metasomatism that can be affected by that process. So at MLD depth, less than 10% amphibole, less than 2% sulfide, and maybe less than even 0.2% magnesite can be stable. So volatile bearing mineral phases can explain only 2 to 3% reduction of pH for with straight depth. But in terms of MLD depth, the reduction in GS has been observed up to around even 8%, 10%. So that higher end of MLD, if it's caused by, if it's true observation, it has to be caused by some other cause. It cannot be this volatile bearing metasomatism. So with that, I'll just leave you with kind of a thought, concluding remark, that deep cycling of volatile, especially water, is thought to be crucial for generating continents that are being formed in subduction zones by cycling of water. However, such cycling of volatiles through